Let's take a look at some more of these work integrals. Another example where we can have varying amounts of force depending on our current position is when we work with springs. So a spring exerts more force or less force according to how much tension the spring is already under, which will depend on how far the spring is extended. So I can write this as a formula. Every spring, according to Hooke's law, thank you, Hooke. I don't know who Hooke is, but apparently this is a person who thought a lot about springs. We can express the force required to hold a spring beyond its natural length. In terms of this function, f of x equals k times x. And k here is a positive constant. So we are going to imagine that this spring is parallel to the x-axis and that x equals 0, the origin for my plot here, is going to be located exactly where the spring wants to naturally rest. So no tension at all. 0 seems like a good place to start most things, so I hope that's a sensible choice as I work through this problem. Sensible in your eyes, I should be saying. So if I move the mass out to position x, the force required to hold the spring here will be a force of k times x. The farther I go out, the more force is required. So let's actually use this and set up a pretty common work calculation, work in the technical sense for physics. Let's say that we have a spring and it will require a force of 40 newtons to hold it in a position. We have stretched it from its natural length of 10 centimeters out to 15 centimeters. We have recorded the amount of force with some kind of measurement. How much work will we require to stretch the spring 3 centimeters further? So look at this, we've already stretched our spring out 5 centimeters from where that spring is trying to get some rest. We're going to pull it 3 centimeters more. How much work does that take? So let's set up this problem in terms of functions. Functions are the grist for my calculus mill. I want every single thing to be a function that I will be able to apply derivatives and integrals. So the force required here is k times x, depending on coordinate x. Now, in order for Hooke's law to work, we need the resting position to be at exactly x equals 0. So what we're going to do is we're going to say that we have already stretched out this spring a distance of 5 centimeters, but we are going to record this as 0.05 meters in order to get the units to work out right. So my force function says that f of x coordinate 0.05 is 40. At the position x equals 5/100ths of 1 meter, the force required is 40 newtons. And again, I'm required to use x measured in meters because newtons are defined in terms of meters. You need to make sure the units are working out for this kind of calculation. Well, I would like to have the actual value for this spring constant, right? I want to know what number k is. So I have used this measurement. I know exactly how far my string has been stretched. I know exactly how much force is required to hold it there, unless I let go. So I can put those into my equation and say that 0.5, that's my x-coordinate, times k must be 40. So k must be 800, just a simple piece of algebra. So this calculation is telling me what my spring constant is. And as a non-physicist, I just find this fascinating that we can learn so much about a spring just by taking two measurements. Measure how far we have pulled it out and measure the amount of force required to hold it there. So this is a requisite part of my calculation. To actually know the force function, I need to know the spring constant. What I'm going to do next is I want to find the work required to pull that spring out further. So that will be the next part of this lecture.